In all the previous examples, we said, you know, you have a car on the road there. This is the road. You got a car moving there at a certain speed. We said neglect friction there. What is the work done to increase the speed from, I don't know, V initial to V final? And since the road is flat, we said the work done, the total amount of work done, is equal to the change in kinetic energy, which is the final kinetic energy minus the initial kinetic energy. I'm just reviewing what we did. This is not, we're not dealing with non-conservative forces yet. So that's 1/2 mv final squared minus 1/2 mv initial squared. That's how much work is done by the engine of your car to get your car to go from, let's say, 30 miles per hour to 40 miles per hour. Again, we neglect that the tire is rubbing on the floor and there's friction there. We're losing some of the energy. Now, if you're picking things up, moving them up and down, a box there has a mass, and you move it a height h. Actually, I'll do it. Let's say this is the ground here. This is h final, and this is h initial. The work done to move this box upward, the amount of work done, in this case, because you're moving in the y direction, the change in the potential energy. We used, I think, U last time. We said U final minus U initial, which is mass, gravity, times the final height, minus mass, gravity, times the initial height. Again, no friction. Neglect friction, wind resistance. We neglected all that last time. And we also did when things moves in both directions, the x and the y. We did the water slide. I'll wait till you finish writing. What about things like, again, water slide? You got somebody sliding down the ramp there. Neglect friction, we said. We have a person here sliding. I'll make the water slide has initial height too. There we go. So this person here has initial height. Well, it could be here sliding down, so if you're sliding down, that's the initial height. And you have initial velocity, you're moving down. Down here, as you're moving down, your height at this point, let's say that's the final position here. You have a final height, and you have also final velocity. So we again, if we say neglect friction, we did that in all the problems last time. We used to write neglect friction. And once you see neglect friction, in this case you have conservation of mechanical energy. So the work done, the total amount, if you look at the work here, if you look at the potential energy here, you look at the, I shouldn't say the work done, the mechanical energy at the top, the initial mechanical energy, it's equal the kinetic energy plus the potential energy. And the kinetic energy is what? 1/2 the mass of the person times the initial velocity squared. And the kinetic energy is what? The mass of the person times gravity times the initial height. The final mechanical energy, it's the kinetic energy final and plus the potential energy final, which is 1/2 mass times the final velocity squared plus mass gravity times the final height. And we said, if we neglect friction, what do we know about these two numbers? Remember what we said about the two of them? They have to be what? Equal to each other. So there's no difference between them. The change is going to be zero because they are equal to each other. Well, today we're going to change that story, because when you're sliding, going down that slope, let's say you're a skier or a water slide here, trust me, there's a little friction. These two numbers will not be equal to each other. Why? You will lose energy to friction. As you're sliding down, friction is pointing backward, and that's going to be energy lost when you get to the bottom. You don't have as much as what you started with. You want to see that actually, that experiment will be an easy one to spot there if you take a ramp there, like a skateboard ramp. And they try to make that skateboard ramp really, really smooth there. So it will look like this. And somebody starts from this height, they slide, they don't go to that height. It's supposed to go, if it was frictionless, we'll go the same height, but you see it go there. Next time you come down, you go here. Next time you go up, you go less. Next time you go less, then less, then less, then less, then you're stuck in the middle. Why? Because of the friction. Each time you go a little bit less. If this was frictionless, it becomes like a pendulum. You start from here, you go back there. Start from here, you go back here. Back and forth the whole time, if it was frictionless. That doesn't happen in real life. We'll get something close to it, but it's not going to be frictionless. So how do we deal with them? And that's what today's topic is. Work done by non-conservative forces. That friction force is non-conservative. It's going to make the final and initial not equal to each other. It's going to be a difference between them. Come on. Let's take an example. So, well, before we take an example, we said the total amount of energy, it's actually the work done by the conservative force plus the work done by the non-conservative force. Now let's take an example. Explain what that means. You're on a water slide. Again. I'll give you the initial height. That's a ball, well, it doesn't have to be you. The initial height is what? 2 meters. Has initial velocity of 0. I'm holding a bowling ball right at the top there. I'm holding in my hand. I let it go. Bowling ball is really smooth. There is a coefficient of kinetic friction, mu k. Now we have a friction of a small number, 0.1. And the question is, how fast the ball will be when you get to the bottom here. What's the speed of the ball? What's the velocity, the speed? Now, if this was frictionless, if I didn't have this number, I will say the sum of potential and kinetic at the top equals the sum of potential and kinetic at the bottom. But that's not the case. I have to give you an angle here. Let's say this angle is 30 degrees. By knowing the angle and the height, can anyone tell me the length of that ramp now? What's the length of the ramp? Nothing to do with physics now. Trig. This is what I know. I know this is 2 meters. This is 30 degrees. Now I'm looking for that distance, D. Which trig identity ties this angle to that side and this side? Is this side the adjacent? Is it the hypotenuse? Is it the opposite? What is it? Opposite, and this is what? So which trig identity? Sine, yep. Sine 30 degrees equals the side that's opposite over the hypotenuse. Now, to cancel the fraction, you multiply both sides by d. Sine of 30 is 0.5, d times 0.5 equals 2. Can we get what d is? 4 meters. So let's look at the top. How much mechanical energy I have at the top? E, at the top. That's the kinetic energy at the top plus the potential energy at the top. How much kinetic energy at the top do we have? It's 1/2 the mass times the velocity squared. I forgot to give you a value for the mass, but I'm not going to give you one. Since I started, I'll leave it. Plus, well, you know what? Just to make, I don't need it. I can do without it, but just to make this problem a little bit easier, let me give you a mass for now. Maybe the next one I'll leave it out. How heavy a bowling ball? Like 5 pounds? Let's say 2 kilograms. Mass times gravity times the height. So it's 1/2 times the 2 times the 0 squared plus the mass, which is 2, 9.8 times the height, which is 2. Is that 39.2? That's the top. How much mechanical energy at the bottom? It's the kinetic energy at the bottom plus the potential energy at the bottom. Just like we did last class. The kinetic energy at the bottom is what? 1/2 the mass times the velocity squared plus mass times gravity times height. 1/2 times 2 times v squared plus 2 times 9.8 times, what was the height at the bottom? 0. So guess what we have? V squared. Now, if I didn't have any friction, if there was no friction left there, then these two will be equal. If this says neglect friction, I'll set these two equal to each other and solve it for the velocity. But not in this example, not today. That was yesterday. Today we have a friction. If I know the value of that friction force, then I can reduce that number by that much because I'm going to lose some of the energy. You're sliding, notice you're moving down, the friction is backward. There's a 180 degree backward. That's a -1. Let's look at that friction now. This is my ramp. This is the ball. There's the normal force. We changed the name. Instead we used to call it N last time. We decided to call it Fn, F normal. We get the friction force, pushing backward, kinetic friction, Fk. And if you remember, friction force is what? Mu k times the normal force, or F normal. What else we got? We got the weight, which is straight down. These are the three forces. So if I make this, and this kind of review actually for your test 2. If you make this your y-axis, and this one your x-axis, notice the weight now, the weight is kind of crooked there. It's not on the x or the y-axis. So if I turn my sheet of paper this way sideways, and I go x-axis, y-axis, I get the normal, F normal, which is up this way. I get the friction force, Fk, which equals mu k times the normal force. Also, I get the weight down here, mg, and this angle is also theta, 30 degrees, that angle. If this question was in our book, this would be a 3-dot or 4-dot question, because there's multiple layers. Notice we had to calculate the distance. That's one of the things we had to do. Where was it? Right here. We had to figure what D is, so that's 1 dot. We had to calculate the kinetic and potential energy for each one. That's 2 dots. We had to figure out what the friction force, that's 3 dots. Every step is a dot in our book. So I'm going to take this force now and break it down to x and y component. That's what I've done in the past. Any force that's not on the x or y axis, I'll find its components. I'm going to have a component in this direction, and I'm going to have a component in that direction. Since this one is, notice, adjacent, that's the cosine, mg cosine theta, cosine 30 degrees, and this is mg sine 30. So that's review for your test. Now, test 2. We know the mass. The mass is what? 2. Gravity is 9.8 times cosine 30 degrees. The bottom number is 3.02. This one, mass is 2. Gravity is 9.8 times the sine of 30. Oh, you know what? Let me correct these numbers. I changed the mode last night to radian. I'm in degree mode now. Let me go back and redo this number. I knew that last night. I said, watch, I'll screw it tomorrow. The mass is 2. Gravity 9.8 times the cosine of 30 degrees. 16.97, about 17. And this one, the mass is 2. Gravity is 9.8 times the sine of 30 degrees. That's a 9.8. Okay. Well, that ball was sliding down. That bowling ball was rolling down, so it was not moving in this direction. In the y direction, there was no movement. It wasn't bouncing like this, like a basketball. That tells me the normal force has to equal 17 Newton. Has to equal to that number. And if I know the normal force is that number, I know what the friction force. It's mu k times the normal force, which is mu k is what? 0.2 we said? I forgot that one. Is it 0.2? 0.1, the coefficient friction. 0.1 times the 17 That's 1.7 Newton. So what is the work done by the friction, the non-conservative force? Well, work is force times distance. Work, if you remember, F times D times cosine theta. The force is 1.7. The distance traveled, we just calculated that. The friction force was 4 meters long. You slid from the top to the bottom. That distance was 4 meters. That's why we calculated that. Times cosine 180 degrees. And that would make it a negative number. 6.8 negative. Negative, which means we lost that energy. That's the heat, the friction. When you rub your hand, that's energy lost. When you're coming down the slide, if you go on a water slide, when you get to the bottom, you feel your butt a little bit warm there from that friction. That's energy lost. So what happens when you get to the bottom? You had that much energy on the top. You lost 6.8. Guess how much you still have on the bottom? The difference between the top and what you lost. So how much energy, mechanical energy at the bottom? It's going to be whatever you had at the top. Oh, I don't know why I use sigma. It's the amount of energy you had at the top minus, or add to it, because that's a negative number. Non-conservative. So it's going to be what? 39.2 minus 6.8. That's equal. It looks like a minus sign. So 39.2 minus the 6.8. So what's that number? So when you get to the bottom, you only have 32.4 joules left with you. And we already figured out on the bottom, my mechanical energy should equal to V squared. I did that early. It's the sum of kinetic and potential, and came out to V squared. So at the bottom, I said the two of them equal to each other. 32.4 equals V squared. What is V equal to? The square root of that number. 5.69, 5.7. That's how fast it's moving. Not as fast if it was frictionless. Notice, I just want to show you, if you treat that as frictionless, that's why a lot of times we say, I just make sure it's frictionless. If you treat them as frictionless, these two numbers are equal to each other. Guess what the velocity is going to be? 39.2, take the square root of that. Oh. If it was frictionless, it would be 6.3. But the fact is not frictionless, it's going to be 5.7. You lost some of the energy to the friction force as you're coming down. Now, normally, like water slide, roller coaster, that coefficient of friction is way less than this number even. So you're really not losing a lot there. You look at the numbers, I didn't lose much. But in reality, it's never frictionless. You will never get something pure frictionless. As I said, the closest thing for us frictionless is ice skates, blades on the ice. Coefficient of friction very small. I think when we looked at that, it was 0.01 or 0.1. Play pool, the ball rolling on that table, that's almost frictionless. Very smooth. The ball is very smooth there. The tablecloth is really soft there. Not much friction there. To us, that's close to frictionless. The glider you saw in the lab when we did the lab, that fancy glider, that's almost frictionless. But in real life, it's not really frictionless. And give us about a couple of years on them, on this equipment, the friction coefficient will increase by a lot more. Just like you take a penny, it looks shiny. And a year later you grab it, go, oh, God, there's so much stuff on that penny. What happened? The exercise. Put it out there, stuff starts to build on it, we touch it, stuff gets on the track, and that's what's going to happen in the lab. As good the equipment is, eventually that coefficient of friction will increase there. Let's take a little more examples with friction. So notice there's more work to the friction. It's not as like we did before. It makes it more challenging now. You got to go back, coefficient of friction, all the good stuff. The good thing about, again, we're reviewing now for test number 2. Let's take another example. We have a tree here. And a leaf falls off a tree. Here's a leaf, fell off the tree, it went straight down to the ground, it didn't go sideways. The mass of the tree is, the mass of the leaf, we don't care about the tree, it's 17 grams. Well, if you drop a piece of paper or a leaf, they don't fall just like dropping a pen, they float. Why? The air under them is pushing up, like parachute. When you see people jumping out of a plane, why they don't fall to the ground? Because that parachute actually, the air is hitting it and slowing you down. That's the same thing. So this is not a free fall. So we do have friction. We can't neglect it here. You can see the paper just floating there. So what do we know? If the initial height is 5.3 meters, we know this was initially, it's going to the ground, so this is ground here, 5.3 meters. And its speed on landing, when it hits the ground right here, the velocity, notice we assume this one has initial velocity of what? It was attached to the tree. What was the initial velocity? 0. When it gets to the bottom, the final velocity for that, before it hits the ground, was 1.7. And the question, how much non-conservative work done on the leaf? So what is the work done by the non-conservative force? Which means the friction, the wind resistance, the wind pushing it. I don't know if you watch that show, you see these people wear these suits. And in this suit, the legs actually, there's a plastic connecting the legs together. In the arm, when they open their arm, you'll see that big cloth right there, and they can glide up in the air, float. I don't know if you've seen them. People jump from a building, from a mountain, and they'll be gliding, flying. Well, that works just like the parachute. The wind hits it. That's why they're attached together. That piece to that piece, it makes like a canopy. And it keeps you, eventually, you got to pull that parachute. I don't think they just land on their feet. If they do, they're nuts. You got to be a massive chute. But it slows you down. And the reason it slows you down, friction. So the friction comes here from the non-conservative force. How much work is done by that? Well, let's look at the top and see how much mechanical energy we had. Let's look at the bottom and see how much. And the difference between them is the work done by the non-conservative force. Now you think about it. When the leaf is coming down, which way the wind is pushing? The leaf is falling down, the wind is pushing upward. So that's going to lose some energy. So when you get to the bottom, you should have less energy with you than what you had at the top. So the work done by the non-conservative force is the mechanical energy at the top minus the mechanical energy at the bottom. What's the mechanical energy at the top? It is the kinetic energy at the top plus the potential energy at the top. And what is at the bottom? Is the kinetic energy at the bottom plus the potential energy at the bottom. The difference between them, it's the work done by the friction force, by the air, the non-conservative force. Let's look at the top. Kinetic energy, it's 1/2 the mass, which is 17 gram, 0.017 kilogram. Gotta convert it to a kilogram. Times the velocity, which is 0 squared, plus 1/2 times 0.017. Oh, I don't know why I said 1/2. Mass times gravity times height. Mass, gravity 9.8, times the height, which is 5.3. That's the top. Minus, let's see what we had at the bottom. Kinetic energy, 1/2 the mass, 0.017, velocity 1.7 squared, plus the mass, 0.017, gravity 9.8. And what's the height here on the bottom? How high above the ground? 0. So mathematically, this is 0, that one's 0. So what we have, 0.017 times 9.8 times 5.3, we had 0.883 minus, let's see what we have at the bottom, 0.5 times 0.017 times 1.7 squared, 0.025. Notice really the friction is not that much. The work done by friction, I mean, in this case, because it's, I shouldn't say that much, it's a lot. Notice the difference between them. We lost a lot of it. When you get to the bottom, you almost nothing left there. A piece of paper will float just like a parachute. It comes out so slow there. So what's left is not a lot there when you get to the bottom. 858 joules. That's the work done by the wind, by the friction, which is almost all the energy that was in the leaf is gone now. We lost it. When you get to the bottom, that's all you have with you. And once it hits the ground and stops, there's nothing left. There's no potential and there's no kinetic. This is right before it hits the ground. Once it hits the ground and sits there, there's no energy left in it. Potential is 0, kinetic is 0. So all of it's gone. But that's the amount of energy lost by the non-conservative force. And what I should have put there, that's what's lost. So to indicate it's really lost, I should have put what? Minus. I should have wrote the question even better. You know what? I should have wrote it better there. I should have reversed that. I should have said it's the final minus the initial, isn't it? Not the difference. It should have been a minus here, because you're going to lose that number. I'm just telling you how much we lost. That energy is lost. So if you want to get the negative sign all the time, what you want to write is the correct way of doing it, because you know you lost that energy. The energy lost, it's equal to the final minus the initial. And the final in this case is at the bottom, minus the initial. So if you did that, your answer automatically, mathematically, will be what? Will be 0.025 minus 0.883, and the difference between them always comes out negative. The energy lost to non-conservative force is always a negative value. So that will take care of the minus sign automatically for you. If you want to do it the way we did here, so this what's on the top, this what's on the bottom, the difference between them is the energy lost. Not just stick a minus sign at the bottom, that's fine. But you might forget to put the minus sign here, and they will mark it wrong. So to be on the safe side, safe bet, always put the final minus the initial, which is in this case the bottom minus the top, and that makes the answer negative automatically for you. Like if you look at the previous one, I subtracted that. I know the bottom is going to be less. So I went to here minus that energy lost. I subtracted myself. but this one does it for me. Let's take another example. Today is supposed to be 88 degrees. And if you think this is bad, don't complain. Arizona and Palm Springs, they had 123 degree weather yesterday. Temperature, 123. So there's the water. You're going to be at the water park. It's a deep diving pool here. And somebody's standing on the diving board. Notice my water's blue here, spotless. There's a diving board. And somebody's standing on the diving board. Now let me give you some numbers about this. This person is 95 kilogram. So the mass of this person is 95 kilogram. Steps off a diving board. Steps off a diving board. What's the significance of that statement? If you step off it, which way are you going to fall? Straight down. So what was your initial velocity in the x direction then? Your initial velocity here, in the y direction, I mean, that's what I mean, up and down, is really 0. You weren't moving. You didn't jump up. It wasn't like you seen these divers where hit the board and they bounce up in the air. It just, this one just fell, just like taking a rock and dropping it. What else do we know? That actually the diving board is 3 meters above the water. So that distance to the edge of the water is 3 meters. Notice these pools are designed where it's really deep, so when you jump in it, you rarely hit the bottom. Because what happens as you start to go through the water, what happens to your body? There's a friction force. You're going through the water, pushing down on the water. Guess what the water's doing? There's a friction force pushing on your body, going upward, pushing you upward. Friction, slowing you down. So you never get to the bottom. It's designed that way. If you make that pool only 4 feet deep, you'll break your legs. You need a lot of water, maybe 10 meters deep, 8 meters deep, to make sure you don't get to the bottom. Let's assume somebody gave us the work done by the non-conservative force. That's the friction. Should be a negative number. It's negative 5,120 joules. So as you're traveling through the water here, the friction rubbing against you, you lost 5,120 joules of energy. The question is, how deep did you travel? What is D? And D is the distance to your feet from the surface of the water. That's D. Okay, let's see. If I use this, the surface of the water, as reference, let me label the spot. What should we call them? The top here on the board, 1. And let's call the spot here spot 2. Let's see the mechanical energy at 1. When you're standing on that diving board, when you're just standing there, going to step off, we have kinetic energy and we have potential energy. What was your kinetic energy? Your kinetic energy is 1/2 your mass, which is what? 95. And your velocity at the top, what was your velocity? 0, and square it. Let's add to it your potential energy, which is the mass, 95, gravity, which is 9.8, and your height is above that reference point, so it's positive 3 meters. Do the math. (95) times 9.8 times 3, which is 2,793. Is that correct there? 95 times 9.8 times 3. 2,793 joules. Okay. Right before you hit the water, let's call this point, you know what? Let's call this 3 here. Let's call this one 2. Right when you touch the water, right when you touch it, that's spot 2. What is the mechanical energy, the total number there? What do you think you have? If we neglect the wind here, neglect the wind in the top part, the wind is not going to slow you as much as water. So when you go through that, how much energy is lost? If you neglect that, right here, again, should be what? 2,793 joules. If we neglect the wind. If not, then that's a different story. Well, it doesn't say neglect the wind here, so I don't want to make that assumption. I don't want to say, well, you know, I'm going to assume the wind is not a factor. Well, it didn't say that. But if it does say that, then your energy here is this. It doesn't really matter if you know this or not. That doesn't change the solution of this problem. I just wanted to point that out. If we neglect the wind, when you hit that water there, you'll have that much energy, conservation of energy. Once you get through the water, the water start pushing on you, and now it's going to slow you down. This is the same thing when you're trying to nail a nail into a piece of wood. You're hitting and it's going slow. Why? Because the wood is pushing back on that nail. There's a friction. And depends on the wood. If it's oak wood, that's really hard wood. It's a larger friction force. If you get a pine wood, that's cheaper, like it's softer there. The nail goes through if you hit it hard. So, but let's look at the bottom, spot 3. What do we have at spot 3? Let's look at the kinetic energy at 3 plus the potential energy at 3. The kinetic energy, it's 1/2 the mass of the person, which is 95, and the person's not moving. We're looking for the distance. That person stopped going down. So the distance, your velocity is 0 here. Potential energy, it's the mass. Now let's think about this again. You're traveling down, so it's the mass, which is 95, gravity 9.8, and your distance is negative d. You went below that line. I'm using that as reference. You went below it, so it's a negative d. We do the math. What do we have? 95 times 9.8, which equal to what? 931, negative 931D. I just said if you want to get the sign correct, the work done by the non-conservative force should be the final value minus the initial value. I'll use E final because I'm using E here. The mechanical energy final minus the mechanical energy initial. The final, so that number was given to us. It's what? Negative 5120. The final is this one. That's the final, that's your initial. You started here and you stopped here. That's your final spot. How much mechanical energy? Negative 931D. Minus the initial value, how much you had at the top? 2793. I didn't want to touch this because the problem never said neglect the wind here. It never mentioned that. So I'm not going to make that assumption. So I'm not even using that. If it did, I can look at it that way. So let's do the math now. Bring this number to this side, becomes a plus. 2793 minus 5120, negative 2327, negative 931D. Can we get what D is? .5 meters. So you probably want to make that pool, most pools, what, 8-10 feet, like the diving one's probably 10 feet deep. 10 feet. How many meters is that? If it says 2.5 meters, you always want to have a safety just in case. You don't want to make it 2.5 on the money. Why? You might be wearing a suit that's really slippery. That changes your friction force. Some people have hair on their body, their back and chest covered with hair. That will change the friction. Some people, some of the divers shave their entire body when they're swimming. That's actually less friction. So to make sure that's safe, maybe I want to make sure the depth of that is like 3 meters, 3.5, 4 meters, just be on the safe side. So if we make it 10 feet, a yard is what, 3 feet? That's 3+ feet. Yeah, you have an extra yard, this much water below you. So even if you make these adjustments to your body, even if you hit the floor, it's not going to be like a hard hit. It's going to be just a little tap there. It's not going to break your leg. So most actually diving boards, if you go to high school, you'll see probably 10 feet, 12 feet deep in the deep end with the diving board. Now if you're jumping from 10 feet high, it better be more than that. I mean, if you jump more than 3 meters high. 3 meters is about roughly 10 feet, you know. Sometimes you go to the circus and people jumping from, God, you look at the tower like, they're going to land in that? Good luck, you know. First, you couldn't pay me enough to jump into it. I'm not afraid of height, but oh no, water's hard. I just watched a show on TV and the guy is actually one of those BMX bikes. And he set up this ramp in his yard to practice. As he hits the ramp, he has a pool, he lands in the pool. And his wife is terrified of doing it. So to make sure he doesn't get hurt, they put a bubbles on the bottom so the water is actually bubbling where you land. And you go, what is that going to do? When the water is flat like this, like hitting a piece of glass. When you hit it flat, like if you land on your back, it's going to hurt. Some of you probably ever jumped in the pool that did a belly flop, and you land on your stomach, your back, oh, you come out, it's all red. It's hard. By putting the bubbler, you break that surface. Not as hard as actually if it was just smooth. Oh, it does make sense actually. Start thinking about the physics. Oh, the guy's actually sharp. It's not just a good BMX guy, but he knew that. If you turn the jets on, when you land, it doesn't hurt because you broke that surface. Not even. Let's do something, who knows, you might see on the test tomorrow. So here's an example, again with the friction. I will look at the clock. Okay. We have a table. You saw this, I think, on the previous homework. I think I had that. We had a table. We did that in the lab, too. This is my table. On the table, we had a block. I think that was our lab last time. We had that cart. We had a string attached to it. And we dangled the weight. Remember that one? That's what we did in the lab. So let's give you some numbers. So the one on the top is 2.4 kilogram. Attached to a string attached to this one, and this one we hung there is 1.8 kilogram. The one we did in the lab was frictionless. So now we're going to add friction here. When the block are released from rest, what does that mean? What's your initial velocity here? 0. What's your initial velocity here? 0. Nothing was moving. They moved through a distance of 0.5 meter. So basically this one dropped. Initially, this was right here. And it moved that way. And this one moved down here. That's what happened. The distance traveled is 0.5 meters for both. They attach with the rope, so if this one moves 0.5, that one moves 0.5. Then stopped. Stopped because of the friction. Or actually, this one hits the floor. This is the floor. That's why it stopped. Stop pulling. Let's assume the coefficient of kinetic friction is 0.450. The coefficient of friction 0.450. Mu k. 0.450. I don't have to put the 0. And what's the velocity right before it hits the ground? Right before. What was the velocity of that? So again, initially this has a speed of 0. This one goes to the right, this one goes down. Before it hits the ground, this has a velocity of v. This has a velocity of the same number. Because again, there's a string attached to them. If this is moving 5 miles per hour, that one is moving 5 miles per hour. And what is that velocity? So this is case 1, the initial for this and the initial for that. This is case 2. This one moved 0.5 flat. This one moved 0.5 down. There's a friction force. So we're going to take the final minus the initial, and that's the work done by the non-conservative force. There's no friction on that end. It might be easy if I look at them as two different problems. Look at this as one problem. Look at this as one problem. And look at the numbers before and after, case 1, case 2. Otherwise, you might get confused. So let's look at the top half of just the ones on the table there. So the thing was here, it has initial velocity equals 0. It was sitting on a table. The table has a height, but they never mentioned the height of the table. Doesn't really matter in this case. This moved 0.5 meters. And this is, again, 1, this is 2. It now has a velocity. We're not sure what that velocity. So let's see. At point 1, What is the mechanical energy? What's the kinetic energy plus the potential energy? Kinetic energy is the mass, which is 1/2 times m, the mass, 2.40, times the velocity square, the kinetic energy is the mass, gravity 9.8, times the height, which was not given to us. So what's that number when we do the math? (2.4) times 9.8. That's actually equal to 23.5 times h. Let's look at the block as it moved from here to there. Now it has a speed. The speed is what? Kinetic energy plus potential energy. It's 1/2 the mass, which is 2.4. We don't know what the speed there. We're looking for it. And what's the potential energy? 2.4 times 9.8 times the height. He's still on that table, the same table. It's 1.2 v squared plus 23.5 h. What is the change in the mechanical energy for these? The difference between them, when you subtract them, it's the final, which is 2, minus the initial, which is 1. And you end up with 1.2 v squared. That's the change in the mechanical energy. But we also have friction there. We'll deal with that soon. Let's look at that glider on the top. Let's find where that friction force is. We get the string pulling in that direction. That's T. We get the weight down, which is mass times gravity, 2.4 times 9.8, and that's 23.5. And we get the normal force up there. And we get the friction force backward. Since this is sitting on the table, moving to the right, not up and down, that tells me the normal force has to equal to 23.5. This has to equal to this. What else? The kinetic friction is mu k times the normal force. Mu k is what? 23 point, mu k, I put them backward, but I'll fix it. Mu k is 0.45 times the normal force, which is 23.5. .45 times 23.5. It's 10.6 roughly. That's the force in Newton. And now, what's the work done by the non-conservative force? It's going to be a negative, because going to the right, the friction to the left, the force times the distance, 10.6, travel a distance 0.5 meters, which is negative 5.3 joules. Just for the top part. I didn't even get to the side. Now let's look at the one up and down. So I want to do everything while I'm looking at it. So for this one, the work done, or the change in mechanical energy, the final minus the initial, is this minus that. Or if I take what at 1, if I take whatever energy I had at 1, which is, where's a 1? We had that number, add to it this number, it should equal what we had here. But now let's look at this one, up and down. So the up and down now, here's my story. This is 1. This is 2. I'm using this as reference. This has a mass of 1.8 kilogram. This has initial velocity equals 0. Don't know what the final velocity is. I know the distance traveled is 0.5 meters. Now again, let's look at mechanical energy at 1, which means the kinetic energy at 1 plus the potential energy at 1. How much kinetic energy we had here? 1/2 the mass, which is 1.8 times the velocity squared. Add to it the potential energy, which is the mass. Gravity 9.8 times the height, which is 0.5. Do the math. I got what? 8.82. What about a spot 2? Kinetic energy at 2, potential energy at 2. So kinetic energy is 1/2 the mass 1.8 times the velocity squared, we're looking for it, plus the potential, which is the mass 1.8 times gravity 9.8 times the height, which is 0 there. There is no friction here. So friction is not a factor here. It's dangling in the air. It's not rubbing on the table there. So now the change in energy is the final minus the initial. 0.9 v squared minus 8.82. So now let's put the two of them together. If we take the change here and the change here, so this is the total change. It's the change for the top one plus the change on the bottom one. Not bottom, side, I think. On the right side. I did this twice. If you combine the two together, it's the top and the side. The top one, the delta was what? 1.2 v squared. Add to it what's on the side, the change. And that should equal to what? 2.1 v squared minus 8.82. What can we do with that? That's the work done by the non-conservative force. So the work done by the non-conservative force, we calculated that number, negative 5.3, should equal to 2.1 v squared minus 8.82. And you end up with 3.52 divided by 2.1, roughly 1.7, and v will be the square root of that number, which is 1.29 or 1.3 meters per second. Whew, that's a lot of work. That is a lot of work. So I had to look at the top, look at the side, how much change in mechanical energy, how much change in mechanical energy, and the difference between the final minus the initial is actually the result of the friction force, the work done by the friction force. So once you set them equal to each other, you can solve for that velocity. Okay, that's it.